Welcome to PFT Tutor with Jeffrey Haynes. In this video, we'll review the interpretation of a diffusion capacity test. DLCO is one of the more complicated PFTs, both technically and physiologically, so in this video, we'll discuss the fundamental ideas needed to properly interpret a DLCO test. So let's do a quick overview of the single breath DLCO maneuver. The patient is instructed to exhale fully or as close to residual volume as possible. Once the patient has achieved this, they are switched into the system and they are instructed to rapidly inhale the DLCO test gas to inflate the lungs as closely to total lung capacity as possible. The inspired volume should be at least 90% of the patient's best vital capacity, and the patient should achieve 85% of the inspired volume in less than 4 seconds. The DLCO test gas typically contains a carbon monoxide concentration of 0.3% and a tracer gas that's not soluble in blood. Methane is used for rapid gas analyzers. Helium is used for systems that collect an alveolar sample in a collection bag, and the older systems using a gas chromatograph use neon. The tracer gas is needed to calculate the carbon monoxide concentration at the beginning of the breath hold. Yes, it's 0.3% in the tank, but once the patient inhales it, it becomes a lower concentration because it is diluted down by the gas you can exhale, your residual volume. The tracer gas is also needed to determine the lung volume that was ventilated with the DLCO test gas. This is called the alveolar volume using the acronym VA. The patient then holds their breath passively for 6 to 8 seconds. The software will open the expiratory valve and the patient is instructed to exhale rapidly. The dead space or washout volume is discarded into the room and an alveolar sample is either analyzed in real time or collected for analysis. The alveolar sample must be analyzed or collected within 4 seconds. You may see the term breath hold time, but the more accurate term is diffusion time, because this time starts at 1/3 of the inspired volume and ends at the point where half of the alveolar sample has been analyzed or collected. This is known as the Jones-Meade method. During the breath hold, the alveolar concentration of carbon monoxide should rapidly decay as the carbon monoxide diffuses through the alveolar capillary membrane and binds to hemoglobin in the red blood cells. A reduced decay of the alveolar carbon monoxide concentration often reduces the measured DLCO value. Let's review the components of DLCO, and the easiest way to do that is to examine the formula used to calculate DLCO. So the DLCO is the alveolar volume divided by the product of the diffusion time and the atmospheric pressure minus the pressure exerted by water vapor. This is then multiplied by the natural log of the alveolar concentration of carbon monoxide at the beginning of the breath hold divided by the alveolar concentration of carbon monoxide at the end of the breath hold. In North America, the DLCO is expressed as mLs per minute per millimeter of mercury. In Europe and some other places, DLCO is often expressed as millimoles per minute per kilopascals. Pay attention to the unit of measure used in PFTs because it expresses what is actually being measured. So DLCO is the volume of carbon monoxide transferred into the pulmonary capillary blood as a function of time and pressure. In some countries, you may see the diffusion capacity referred to as TLCO, CO transfer factor, which I think is actually a better term because DLCO increases with exercise and we measure it at rest, so it's not really your capacity. When we're learning about DLCO, it's natural to focus a lot of our attention on the changing concentration of carbon monoxide. CO is right in the name of the test. However, it is important to understand that the alveolar volume is a very important component of DLCO. It's not all about the change in carbon monoxide concentration. The alveolar volume, or VA, is calculated by multiplying the inspired volume minus the dead space by the inspired concentration of the tracer gas divided by the expired concentration of the tracer gas. If we then divide the DLCO by the alveolar volume, we will be left with the transfer coefficient. The transfer coefficient uses the acronym KCO. Now, some of you may still have the DLCO VA displayed in your software or on your reports. This acronym was thankfully abandoned in the 2017 ERS ATS DLCO standards because it created a lot of confusion about what this value really means. It is not the DLCO adjusted for alveolar volume. So when we're talking about transfer coefficient or KCO, we're not considering the alveolar volume component of DLCO, and there are a number of conditions that can reduce the KCO, including decreased perfusion from conditions like pulmonary embolism and pulmonary hypertension. That will reduce the ability of CO to transfer into the circulatory system. It's not part of this graphic, but anemia and carboxyhemoglobinemia will also have a negative impact on KCO because the carbon monoxide has to bind to hemoglobin. A thickened alveolar capillary membrane, as you'd see in patients with interstitial lung disease, will reduce KCO, and a disproportionately high lung volume to surface area, as you'd see in emphysema. KCO can also be high, sometimes above the upper limit of normal. Conditions of increased perfusion like tachycardia and exercise will increase the KCO. In fact, failure to increase KCO during exercise is not a good prognostic sign. The KCO could also be high if there was a thin alveolar capillary membrane. And lastly, from a reduced lung volume to surface area ratio, and the most common condition here is neuromuscular disease, where the lung parenchyma is completely normal, but the alveolar volume is reduced due to muscular weakness. So with the preserved surface area, the carbon monoxide rapidly transfers into the capillary blood. You may also see this if the patient doesn't inhale close to their TLC during the test. So there are two equally important components of DLCO. The alveolar volume, the volume of parenchyma that was ventilated with the DLCO test gas, and the transfer coefficient, the KCO, the rate at which the carbon monoxide disappears from the alveoli into the circulation. Earlier I showed you the formal equation to calculate DLCO, but the easier way is just to multiply the KCO times the alveolar volume. Let's look at this example from a patient with a normal test result. So the KCO is normal at 4.43 with a z-score right around 0. And if we just multiply it by the normal VA of 6.15 liters, we get a DLCO of 27.2, which also has a z-score of almost 0. We use reference equations for each component. So there's an equation for alveolar volume, there's an equation for KCO, and their product, DLCO. As shown by the red lines, the KCO really doesn't change much over the lifespan. There are relatively similar values for children and adults. The age-related increases in DLCO are related to the increasing number of alveoli that are developed during lung growth. As you can see, the age-related increase in DLCO mirrors the age-related increase in alveolar volume. Let me illustrate this point a little further. Here are two DLCO values from a 27-year-old female on the left and a 7-year-old female on the right. They both have normal DLCO with almost identical z-scores just above 0. The 27-year-old has a DLCO of 19.76 and the 7-year-old has a DLCO of 12.47. As I showed you earlier, despite their 20-year age difference, they have essentially the same KCO values. The reason why the 27-year-old has a higher DLCO is exclusively due to the fact that she has a higher alveolar volume. She has bigger lungs. They function the same, they're just bigger. She has more alveoli. Okay, let's shift gears and look at some examples of not so normal DLCO results. This is a patient I tested who developed hypersensitivity pneumonitis from exposure to bird droppings. These used to be called bird fancier's lung. You can see the obvious interstitial disease, honeycombing patterns, and emphysema. His spirometry showed very severe restriction with the classic restrictive flow volume loop. Lung volume testing also confirmed restriction with a TLC 6.4 z-scores below 0. Both his KCO and his VA are below the lower limit of normal. In fact, his VA is so low it doesn't even fit on the z-score graph. So if we take the KCO of 3.36, multiply it by the VA of 1.59, you get a DLCO of 5.3 with a z-score over 8 scores below 0. It's also off the scale on the z-score chart. This patient was actually intubated the day after I tested him. He required ECMO and eventually received a double lung transplantation. And I see him regularly for surveillance spirometry, and he's doing fantastic. Let's look at another patient with restrictive lung disease, albeit with a very different pathology. This patient also has a restrictive pattern on spirometry with both FVC and FEV1 below the lower limit of normal, but a normal FEV1 to FVC ratio. Restriction was confirmed with lung volumes. The TLC is well below the lower limit of normal. This patient also has a DLCO below the lower limit of normal and a low alveolar volume, but the KCO is above average. Not above the upper limit of normal, but it's definitely out of proportion to the VA. So how can you have a low DLCO but a rather high KCO? Remember back to our discussion of the mechanisms leading to an elevated KCO. This patient has neuromuscular disease, so his lung structure is normal surface area, but the alveolar volume is low due to muscular weakness. When you expose a small amount of DLCO test gas to an alveolus with normal surface area, it will transfer into the circulation rapidly, thus resulting in a higher transfer coefficient, or KCO. Based on this phenomenon, sometimes a normal KCO could be considered abnormal. This is the patient with interstitial lung disease who has a very low alveolar volume and a normal KCO. However, if you reduce lung volume of normal lungs to this degree, the KCO would be elevated. The KCO here is normal but below the average with a z-score a little less than 0. So one could consider this normal KCO abnormal because at this lung volume it should be elevated, not average. As the interstitial lung disease progresses, both the alveolar volume and the KCO will be below the lower limit of normal. This is the pattern you'd expect to see in patients with pulmonary vascular disease, so people with pulmonary embolism, people with pulmonary hypertension. So in this example, the alveolar volume of 5.91 is very normal, but they have a loss of KCO because of reduced pulmonary blood flow. So if you multiply the KCO of 2.46 times the normal alveolar volume of 5.91, you get a DLCO of 14.5, which is below the lower limit of normal. Here's an entirely different form of pathology. This patient has emphysema on CT, but as shown here, his spirometry is completely normal. And this, in fact, is not very uncommon. This is a study from the University of Vermont published in Chest. They studied 274 subjects with emphysema on CT, and on average, 10% of the patients had normal spirometry. So we have to be careful declaring, oh, your lung function is fine based on spirometry alone. In this patient with normal spirometry but emphysema on CT, the alveolar volume is above average, not surprising, but the KCO is very low due to loss of surface area and probably some capillaries too. When you multiply the KCO times the VA, the DLCO is 12.49, well below the lower limit of normal. It's important to realize that not only emphysema, but interstitial lung disease can be accompanied by normal spirometry, and the only thing that may be abnormal is the DLCO. This is obviously a patient with very severe emphysema. There is a severe loss of FEV1 at 0.45 liters, 13% are predicted. If you follow FEV1Q, it'd be less than 1, and a FEV1 to FVC ratio of 17%. I guess this is unlucky 13 because his KCO is also 13% of predicted, very low at 0.56. The alveolar volume, even though he has emphysema and presumably has a high TLC, is also below the lower limit of normal. And when you multiply the KCO times the VA, you get a DLCO of less than 3. In patients with severe emphysema, and even some patients with severe asthma, you'll start to see a gap between the measured total lung capacity and the alveolar volume estimated during DLCO testing, and this is why. This was the study that was published in the Journal of Applied Physiology looking at patients with severe emphysema. This is a CT image, and it goes anterior-posterior, so this is the front of the patient's lungs going through the patient's chest to the back of their lungs. And they looked at the density of the tissue using Hounsfield units. So Hounsfield is who invented the CT scanner. A Hounsfield unit, it talks about the density, or expresses the density of tissue. So water has a Hounsfield unit of 0, bone would have a Hounsfield unit of 1,000, and air has a Hounsfield unit of minus 1,000. So shaded here in green are the areas of the lung that have Hounsfield units more negative than minus 930. So these are showing areas that are basically there's no tissue at all, it's just air. And this is the reason why you see the gap between the VA and the TLC, is because the DLCO test gas simply can't go to these areas in any meaningful amount or even be emptied from it. And this is also why using plethysmography for patients with emphysema is more accurate than using helium dilution or nitrogen washout, because these represent non-ventilated areas. So examining the alveolar volume from DLCO can help us assess the airflow heterogeneity within the lung. So this is a patient who has severe airflow obstruction with an FEV1 to FVC ratio of 33%. Their total lung capacity is 7.77 liters, and the alveolar volume from the DLCO is 3.57 liters. So right on our reports, we have the VA to TLC ratio right here, and that's 46%. The other way of expressing this is called the poorly communicating fraction, which is this 1 minus the VA divided by the TLC. And so if the VA to TLC ratio is 46%, the PCF is 54%. And the poorly communicating fraction is actually a very good predictor of exercise intolerance in patients with COPD. So as you can see here, you have the PCF percentage on the y-axis and controls. The difference between the TLC and the VA is not very large at all. But as their gold stage increases, you can see in a stepwise fashion that the PCF increases with it. This is a receiver operator characteristics curve. So this is used to judge the accuracy of a test to predict an outcome. And so basically what you want to see is the higher the line here and the more area under the curve, the better. And this line here is the PCF of 33.4%. And that was better at predicting exercise intolerance in FEV1, DLCO, or residual volume. And I have seen this improve with bronchodilator. So in this particular patient, their total lung capacity was 8.68 liters, and their alveolar volume was 6.55, so their VA to TLC ratio was 75%. And then after bronchodilator, you can see that the gap got much smaller, down to 180 mLs, and the ratio is then 0.98 after bronchodilator. Here's another pattern you may see from time to time. This patient has a normal KCO and a normal VA, but when you multiply the two, the normal values produce a DLCO below the limit of normal. So we have a normal KCO of 3.61, multiply it by the VA of 5.65 gives us a DLCO of 20.3, but the DLCO is below the lower limit of normal. This is kind of weird. What explains this pattern? Doesn't seem to make a whole lot of sense. One factor in play here may be the fact that we apply a z-score of 1.64 to DLCO like we do to spirometry data. This is done for standardization. However, spirometry is better suited for a lower limit of normal of minus 1.64 because there's no such thing as pathologically normal spirometry values. So this becomes a one-tailed bell curve where only 5% of healthy patients are expected to have values just below minus 1.64, and 95% of patients are expected to have values above minus 1.64. Since DLCO can be abnormally high or abnormally low, it's probably better to use a two-tailed bell curve with a z-score of -2 to +2, splitting the 5% error with 2.5% on each end. So if we do that in this example, we see that the z-score is -1.96. So if we were using a -2 to +2 as the normal range, this in fact would be normal. Here's another example of this pattern. There's a KCO of 3.30, which is normal. A VA of 3.72, also normal. Multiply the two, you get a DLCO of 12.2. Its z-score is -2.08, so it's even outside of the two z-scores if we use the two-tailed approach. But we tested this patient a year later, and when the patient came back, there was a slight increase in the KCO to 3.77, a slight increase in the VA of 3.82, and now the patient has normal values. So we have to be careful when patients' values are around the lower limit of normal. There's always some variation in your test results. I know myself as a biological control subject, my number is not always the same. There is some variability, obviously, that occurs. So you don't want to get caught into this trap of declaring somebody sick, and then they're healthy, and then they're sick, and then they're healthy, and then they're barely healthy or almost sick, just because their values happen to be around the lower limit of normal. So lastly, you may have noticed that I haven't discussed this pattern. The DLCO is abnormal, but is normal when corrected for alveolar volume. That's because, in my opinion, this pattern doesn't exist. And this is why the acronym DLCO-VA was changed to KCO. The VA is not the DLCO. The KCO is not the DLCO. The product of VA and KCO is the DLCO. They are both components of the DLCO. And when you divide the DLCO by the VA, there is no volume. You just removed it. It's now the KCO, and that's the transfer coefficient. And you may have a patient with interstitial lung disease like this, where they have an abnormal DLCO and a normal KCO, but this is not normal. And if you have a patient with one lung, that's not normal. Their DLCO will likely be low. They may have a normal KCO, but their DLCO is not normal. Key points: DLCO is not just about the rate of gas transfer, it's also about the volume of gas that's transferred. DLCO VA should be replaced by KCO in software and on reports. Understanding the role of VA and KCO in DLCO is important for accurate interpretation. VA to TLC or PCF may be important to follow, particularly in patients with COPD. And please stop saying that abnormal DLCO is normal when corrected for alveolar volume. Thank you for watching PFT Tutor with Jeffrey Haynes. Please click the like, subscribe, and notification buttons, and we'll see you next time.